Imagine having all of your data at your fingertips all the time. No messy data movement projects worried about network speed or processing power. You just get your data, big or small, in almost no time. Sound too good to be true? It isn't anymore. That's because a company called Hammerspace took a page out of high performance computing's playbook, created a massively parallel marshaling area for enterprise data, and deployed it inside a unified namespace. Find out how on this episode of Future Proof.
The future is here already. It's just not evenly distributed. Yet. Today's world teems with innovation. The nexus of hardware, software, and human ingenuity promises a revolution in possibilities. What does tomorrow look like? Witness Future Proof.
Yours truly, Eric Kavanaugh, is here with a real mover and shaker in the industry, folks. I'm very excited to have David Flynn with us today. He is the CEO and founder of a very interesting company called Hammerspace, and they're doing some absolutely fascinating work. So, in the data world, we've been working for decades to get the data where it needs to be for the purpose intended. Data warehousing was invented largely because people realized you couldn't query these analytical, or you couldn't query these transactional systems. That's not what they were made for. So we pulled all this data out, used all sorts of ETL to move it into relational models, and then enable people to do analysis on it. There have been several movements since then. We've seen VMware come along, for example. We've had the whole Hadoop movement where we tried to fit all this data into the Hadoop, or the highly distributed file system, Hadoop distributed file system, HDFS. But these were all shortcomings in a certain sense. In other words, they never really got to where we wanted to be. And the company we're talking today, Hammerspace, and David has done something that I think may well have solved this conundrum. So, David, welcome to Inside Analysis. Tell us very quickly about Hammerspace, maybe where the idea came from, and what you folks are working on.
Well, thanks, Eric, for having me on. Yeah, Hammerspace, first, the name, we didn't invent that. It's actually a term that has been used to talk about the extra-dimensional space where magicians can pull things out of thin air. So it's like hyperspace for sci-fi and for travel. Hammerspace is for fan fiction and the superpower of accessing an alternate universe in which you can store things. So if you pull something out of thin air, where did it come from? It came from Hammerspace. And we use that term to talk about what we do with data, because now data is no longer bound to the physical universe of storage. It was a very adept analogy that you used with the data warehouse. That is what in the structured data world people use. But here we're talking about unstructured data, raw file data. And the reason why that's relevant is because with AI, we can extract value from unstructured data, images, video, media, documents of any type. It no longer has to be rigidly structured for there to be value. So then the question is, how do we do, the equivalent of what a data warehouse did, but for unstructured data, especially when considering that you can't afford to make copies of it.
Right.
Because this is much heftier than structured data. And so what Hammerspace does is we aggregate data across all of your existing storage and leave the data in place while creating a single logical view and the ability to consume it with extreme levels of performance from where it sits distributed in storage systems. And this allows us to project that data across whole different data centers and now move the data at the swipe of the mouse. So this isn't just about creating a unified logical view to physically distributed data. It's then about being able to control the layout of the data on the infrastructure through policy so that you can manage where the data is going to live. We talk about that as data orchestration.
Yeah, I mean, that's a really, really big deal because historically, as I mentioned, we used technologies like ETL or ELT when the cloud came around. I remember Synopsys, bought by Oracle. They did the ELT. Let's extract, load, and then transform it in the target environment. But you're still just moving data around and around and around. No,
And
my other
again, that's all
show,
structured data. That's not the low-level unstructured file and object data.
right? Well, and that data that you're talking about, the unstructured file data, that's the kind of data that AI really wants to consume in order to train these huge models, right?
Exactly. And you talked about Hadoop because that was one attempt to solve the problem by creating one massive commodity storage pool that you could dump everything into. The only
Hmm.
problem is you're going to access it over Java and through the low performance. It's not a real file system. Hadoop is not an enterprise grade, highly available, feature rich. It's not a file system that the OS can load data from through the POSIX interface. It's not a native thing.
Right.
Um, it's a higher level bolt-on.
Yeah, and I'm glad you mentioned that because when we were talking before the show, you were explaining how you do this. And I think it's quite fascinating that you are essentially deploying an abstraction layer that sits above the files themselves and is a file system that can touch into any given file that it has access to, and then can pull it out into this abstraction layer just like a magician pulls the rabbit out of the hat, right? You
Yeah,
could
yeah.
pull it out and then use it anywhere, which really obviates a lot of the mundane ETL style data movement that we've seen historically, right?
Well, yeah, you explained it very well. We consume storage interfaces,
Hmm.
file-based shared file storage, block storage, object storage, and we present as file storage. That's the most native interface. Also can present as object storage, or in the case of containers, even as block storage.
Hmm.
So think of it as storage interfaces in, storage interfaces out, and what that allows us to do is to present at the lowest level as a real file system. But what makes this truly magical is that we actually accelerate the access to data. Normally, when you add an abstraction layer, like VMware
Right,
abstracted the compute from the very computer running it,
right.
we're abstracting data from the very storage storing it. But because we have used a new architecture that came from the world of supercomputing, of a parallel file system, this allows us to actually unlock trapped performance
Hmm.
inside of the storage systems. So this is a magical case where you add an abstraction layer, which gives you the extreme agility of decoupling the logical from the physical. But in the same process, you're unlocking levels of performance never seen before in the world of NAS, network attached storage, enterprise file storage. Now you get a file system that can access things in bulk parallel at unprecedented rates. That's
Hmm.
why we talk about that as hyperscale NAS.
Wow. That is very interesting because you're right. Typically, a layer of abstraction is going to slow you down.
Correct. Yeah.
But you mentioned, and this is actually very interesting because probably 20 years ago is the first time I noticed that there was this remarkable disconnect between the HPC world and the enterprise data and data warehousing world. And I asked myself, why? Like, why aren't you folks talking to each other? And apparently, you are a manifestation of what I longed for 2 decades ago.
Well, yeah, you are quite right. You had the world of enterprise file data, or NAS, network attached storage, the NetApps, the EMC, Isilon, now part of Dell, newer players like Cumulo or Vast.
Mhm.
Those enterprise file storage are not as fast, to put it kindly, as the world of supercomputer file systems.
Mhm.
These HPC file systems are designed to get a kind of scale that these things can't touch. And fundamentally, by the way, that architectural difference is the separation of metadata from the data and having parallel data path.
Hmm.
Um, think of it like the difference between a DNS server and a, a proxy. Can you imagine if your domain name server that helped you resolve a google.com, say, can you imagine if it had to subsequently proxy every last byte of traffic that went to that domain that it resolved? Your
Wow.
performance would suck. Well, guess what? The traditional enterprise NAS storage world was like that. The thing which opened the file foo subsequently has to be involved with every last IO that goes to the file foo. Metadata and data combined, control plane and data path combined. That's what hampers your scalability and performance, is that your control plane and your data plane are the same. When you separate the two, you can unlock levels of performance, and that's what the supercomputing world has used for a long time. But the stodgy old world of enterprise NAS has not. That's why VAST and Cumulo and Isilon and NetApp and all of these standards-based, plug-and-play, feature-rich and robust NAS have the drawback of having rather poor performance and scalability. Not rather poor, very poor, compared to what you can do with this separation of control plane and data path. Think of it as moving to a routed model instead of a proxied model. Right? But if you ask, okay, why wasn't this done before? The answer is you have to have a much more sophisticated client. The network file system client has to know how to do this routing trick as opposed to simple, talking to a storage server. It has to look aside. It has to do a lookup. It has to talk to a DNS server for data before it goes and talks to the data. It has to know how to work with this split control plane and data path. And that sophistication was not only difficult to build, but can you imagine having to build it for 10 different operating systems?
Jeez. Yeah.
You don't have to now because Linux won. So the reason why this is possible today is that Linux won the OS wars. When it comes to performance and scale, there is only one. You only have to make the one implementation, which is why the first thing I did when I founded the company was recruit the Linux kernel maintainer of the storage networking stack of NFS. And we together built the new standard and the implementation in Linux to teach Linux how to work with this bifurcated control plane and data path, which allows you to then virtualize data from the very storage storing it. And all of that wasn't to unlock performance, although that's one of the ancillary benefits. The reason we did that is to unlock the ability to move data non-disruptively while you're accessing it. Massive petabyte scale data sets can be moving across different storage systems or across whole data centers. That's data orchestration. And as soon as you can do that, now you can have continuous view of and access to data even while it's moving. And this is incredibly important when you're processing with GPUs and doing AI workflows, because you can't afford to have those GPUs sitting there waiting to get their data. So GPU data orchestration is the ability to take data from existing file systems and instantly import it into Hammerspace, project it across whole data centers, and move it behind the scenes while you're already accessing it.
That's crazy. I mean, that's impressive. So you've basically freed the data for use anywhere across the spectrum of the information landscape. I mean, I often joke that some people think they don't have an information architecture. You do. There is a de facto information architecture right now in every company. It may not be very well managed or very well designed, but it's there. And what you're doing is coming in and enabling a fluid information architecture across the entire environment.
And the beauty is, it's not asking people to do a forklift upgrade.
Right.
Because other companies that are trying to provide systems to serve data into, say, AI, ML, large language models, multimodal models, they're saying, hey, you got to buy this replacement storage, right? Hey, we can sell you faster storage. We can sell you, storage that's capable of feeding these GPUs. Hammerspace is a very different story. We're saying, look, you already have a bunch of storage. Add the orchestration layer on top, the hyperscale NAS virtualization layer on top, and now you've got the performance and the agility to move and position the data where it needs to be and to feed it fast enough. And yet the bulk of your data can sit still in the storage where it originated.
Right.
You don't have to do a forklift.
Talking to David Flynn, CEO and founder of Hammerspace, an incredibly interesting technology. I spoke to your VP of marketing a while ago, and she blew my mind. Very, very interesting. Molly, I guess her name is.
Molly Presley, yep,
Molly Presley. She's fantastic.
extremely
And
talented.
I sit around and I think about this stuff all the time, right? So just the other day, literally less than a week ago, I was flying out to Boomi World, our big integration, cloud integration vendor, and I'm just thinking about these foundational models and the history of data warehousing and business intelligence and all these things that we've tried to get to, and how these new developments impact what we were trying to do and how we can do them now. And those are two very, very different things. And one of the thoughts I had is this concept I call the executive cockpit. And here's what I think is going to happen. I think very forward-looking organizations are going to deploy probably a small language model in their data center, in their private data center. They're then going to train that model on their data warehouse data, their ERP data, their Salesforce, their CRM, their customer support, whatever trusted enterprise system data they have, they're going to train this model, fine-tune it. Then you're going to set up Kafka topics from these different systems into a vector database adjacent to the small language model, slap a really snazzy UI on top, and that is how the executives will run their business all day. They'll ask questions like, how is our marketing working in the East Coast? Who do we need to hire next? Which departments are having difficulty right now? And just get all kinds of answers and then take action. Say, okay, computer, set up a meeting for all my regional VPs sometime next week. Here's the list of things to discuss, and please build some charts to show what I'm talking about. Enter, boom. It just goes out there, sets up the meeting, gets the people, feeds them the information. I think that's the future of management of at least large companies. But what do you think about that whole idea? Is that far-fetched, or what do you think?
Oh, no, definitely. I think it's going to take a little bit longer to get there, given the challenges between context windows, being able to, view enough data simultaneously versus what it takes to train on it and so forth. So you're going to have this kind of a natural tension between the, let's call it long-term memory or learning, and the short-term, attention of these systems. There are innovations happening as we speak in these areas, but I think there's still going to be some challenges with having them take over some of that role that you're talking about. But I'm stunned every day at what it's being shown to be able to accomplish. So yeah, at the end of the day, I think you're right. These systems are going to, it's largely going to be interactive, obviously natural language, massive amounts of data at the fingertips. There are other potential challenges beside context windows versus trainings and fine tunings. There's issues of these systems making things up out of whole cloth, and you don't necessarily know if they're imagining something up. So how do you put how do you make sure it's not just daydreaming about things? So you're going to have a lot of the problems that you have with humans, of the fallibility of it, and how do you guarantee it? So I don't think we can leave the, let's call them the we have transactional systems and we have data warehousing systems. These are both forms of structured data. I think those are still going to need to exist, because that's where you can prove that things add up, so to speak. Right. It's not just imagining things. So, we're going to have challenges with AI, because just like with people, it will be fallible in that sense. We're used to having computers be, when they say that the sum is X, it's X, and, doesn't mess that up. You can't necessarily trust that with AI.
It's because it's probabilistic math underneath, right? I mean, you're taking text or images, converting it into mathematical formulae, vectors specifically, and then converting back, sort of encoding and decoding on the other end to reflect back in words or images. So there's going to be a lossy, is how they refer to it in the audio world, right? When you take a recording of a recording, you get this lossy effect where you lose a little bit of the fidelity. But nonetheless, the power is tremendous. But let's get into how you can enable this AI world. So I'm doing some advising.
And how we currently are, like
go ahead.
With Meta. They released Llama 3 just a few weeks ago. Their team uses Hammerspace in the development of Llama 3 in conjunction with their own warm storage, or it's called Tectonic. Think of it as their own object store, their own blob store. Hammerspace provides a very high performance file front end so that researchers can have the convenience of a true file system. You can CD into directories, you can LS, you can move things around, and then it's big enough that you can actually feed a cluster, in their case, 24,000 GPUs in one cluster, and they're going to have dozens of those clusters. Mark Zuckerberg has said they're going to deploy 1 million GPUs. So you can imagine this is the high end of the high end of problem space. And that's why it's so exciting that Hammerspace is being proven out at that scale in not just the ability to move data quickly into the GPUs as a file server, but also the data orchestration, the ability to take existing file data from multiple sources, pull it into the same logical file system by reference instantly. You don't even have to copy data to get it into Hammerspace. You simply point us to those file systems, and we can, in the background, scan all the metadata while you're already using it. So this avoids data migrations to get the data collected up. And then once the data is in Hammerspace, with the swipe of a mouse and change of policy, you can redistribute the data across the physical infrastructure, and you can replicate it to other data centers. And that's becoming increasingly the need, is GPU data orchestration, because GPUs, go figure, they take up a lot of space and power, and they have to be racked and stacked and plug into a power source, which means that the old adage of move the compute to your data is no longer viable. Data is the thing that's virtual, digital. It's what ought to be able to move in the digital. It's the compute that is physically bound to the infrastructure, to the physical world. And so the old wisdom in the computing world, you've probably heard it before, move the compute to the data. Well, that's fine if it's just moving this program to run over here on that server. But if you're talking about a training that takes thousands of GPUs, I'm sorry, you're going to be moving the data to where you have those GPUs.
Right.
So data orchestration
That's pretty funny.
is a prerequisite for GPU-based computing because of the sheer scale of that compute. The data has to do the moving, not the compute. And especially with the challenges of getting availability of GPUs.
Right.
I mean, there's not enough of them.
And Molly talked about that. Yeah, sure.
Right.
Which is a problem.
And then you have the fact that it's a very bursty workload. So even if you could get your hands on them, you wouldn't want to deploy your own just to have them sit there underutilized. So we need a shared infrastructure model, a cloud model. But how are you going to do that if all of your data is on-prem, right? So if we're going to share infrastructure so we can get higher utilization of GPU clusters, now it's even more incumbent on us to solve the data orchestration issue. And copying stuff back and forth isn't going to cut it.
Right.
Well,
you're really giving me some ideas here too about how you can solve one of these other very huge, long-standing, vexing, hitherto intractable problems.
That's the exact term I used.
That's pretty funny. Which is getting a full, clean assessment of what you have, of your data.
The golden copy problem actually goes to a bigger issue, and that is that if your main tool for managing data is to copy it, then you are forking its very existence. It's new data. And now either the original or the new one had better get deleted at some point, but it's hard to do that because you don't know, maybe one has changed and maybe the other's changed. So what ends up happening is it's like cutting off a hydra's head. It just creates more of them. Managing
Right.
data via copy is self-defeating because it just
Right.
makes more data to
That's a
be
quote.
managed.
That's funny. That's an excellent quote.
Well, the
I'll
other
write
thing
you
I like
down.
is the analogy of Captain Kirk in the transporter when he gets split in two. Now, that was the
Right.
good Kirk and the bad Kirk. I guess it was the next generation when Riker got perfectly cloned, and there were two Rikers, and the second one went off to have a career and went off to whatever. And it's like, well, which is the real Riker
Right.
at that
That's
point?
funny.
What's the real data? The very conceptualization of data gets fractured when you copy it.
Mm-hmm.
And it's that golden copy issue. So you have the golden copy issue. You have, well, what all do I have? Especially when there's a bunch of duplicates of the same thing, slightly modified because you've forked it. It just is a nightmare that we can't continue to perpetuate that model.
Mm-hmm. Well, and I can see there are stats out there. I heard one stat that the average document is copied like 4 to 7 times or something in organizations. And there are analytical solutions that require you to take a whole copy of the data and throw it over here into their environment. There are
Mhm,
digital twins, for example, that you have, which sometimes you would want to
mhm.
use for various planning purposes. Lots of different reasons why you do these things, but point being, if you can solve that specific challenge, which is gobsmacking, I mean, it's massive,
Mhm.
with this layer of abstraction, that's a huge deal. And also, just in terms of what you're paying on for storage, right? Like, which data do you use? This is the other thing that's driven me nuts for years, is thinking all this ETL is going around and around and around and around. I've yet to see anyone who can get a strategic view of which data is being moved where, when, such that you could understand, wait, we're doing this 7 times. Like, why don't we just move this data there and then move this data over here? Like, it's just too difficult. It's this big spaghetti monster, basically.
The beauty here is that we've had the opportunity to fix that. Now, you're talking there about structured data systems,
Hmm.
databases where you do ETLs
Right.
and you move
That's
from a
right.
transaction system to a data where, right? Fine. That world, the 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 die is cast. That's the way it is. It's okay. But the world of unstructured file and object data is so far behind that
Yeah.
we actually have an opportunity to do it right, in a sense.
How
Okay.
interesting.
And in that world, we do it by having something, an abstraction layer that consumes storage interfaces and presents self-similar storage interfaces at the lowest level. So it's not up at an object level or an HDFS where you have to access it with Java or with REST
Right.
interfaces. It's a
Right.
true file system consumable by the OS at the most natural layer, network file system.
Right.
Um, but then what we have done is we've introduced a whole methodology for how to express in the data's metadata what the data needs from its physical environment.
So I got to throw a use case at you, David. I've been around long enough to remember actual cameras with film, and you processed, and of course you were very careful about what you snapped because you had to pay to get it processed. And now we have a completely different world where instead you have thousands and thousands of pictures, and someone's going to, oh, I'll show you my kid, and they're like scrolling and scrolling and scrolling and looking for something. I'm guessing with your technology under the hood, and I think Google may have something similar they're trying to do. I'm not entirely sure, but I did notice that you can now search in your pictures like dog or grass
Yep,
or
yep.
something, and there's some metadata that has obviously been captured by an algorithm that scans the images and finds things for you. That's something you'll be able to do, which is incredibly useful in the creative arts for like knowing which picture to find, knowing which picture or which image or which movie, or knowing where in a 2-hour segment of video you show up. That's the kind of things you guys can now enable, right?
Eric, I'm impressed. This was actually one of our early demos, was throwing data into Hammerspace and having it automatically orchestrated like Lambda functions
Hmm.
through image recognition and then tags gathered. And then you could say, oh, by the way, I want all of the pictures that have this person in it or this whatever.
Right.
I need that orchestrated to this site.